I want to welcome everybody to the Kaput Centre's Colloquium series. This is the last talk for this semester, and thank you for all turning up. And today it gives me a great pleasure to introduce two friends and colleagues who have been working together for many years on very exciting software curricular projects around dynamic statistics, data visualization. I'll introduce you Bill first. Bill Finzer is a senior scientist at KCP Technologies, where he leads the Fathom dynamic data software development team. His experience includes software development, curriculum development, and research into programming tools, teacher professional development, classroom teaching, and research on learning statistics. He's currently the co-PI of the NSF-funded Data Games project, which I believe is the focus of the talk today. And Bill's current interests center on developing software and curriculum to prepare students and teachers to make intelligent use of data deluging our society. And Cliff Konold is a PI, principal investigator for the TinkerPlots data sharing and model chance projects. He's based at UMass Amherst. Since 1989 he has directed a number of research and development projects both at UMass and at Turk. Psychologist by training, he studies how people reason and learn about chance and data, and applies this research to the design of educational materials and software. He led the team that created the educational data analysis tool TinkerPlots, which I'm sure he'll be showing you today at some point, and which he continues to develop with grants from the National Science Foundation. For the past 4 years he has been working in public school in Holyoke, Massachusetts, with students aged 12 to 14, trying to teach them something and then figuring out what they really learn. Both the softwares that were focused on Fathom and TinkerPlots have been used extensively here in teacher training programs here in the state as well, and especially in this region, across a wide variety of age groups. So for the teachers in the room, those who haven't seen this software, I hope that it's going to be something that could also potentially impact your practice. But I'm going to turn it over to both of our colleagues first. We're going to spend, they're going to want to spend an hour talking and then leave 30 minutes for question and answer. I'll take any clarificatory questions during the hour, but that's the plan.
The plan.
That's the plan. Over to Cliff.
And I should speak into this. All right. First, thanks very much for having us out here. This is my first time in the Kaput Center. Not my first time in this area, but since this was built, it's a pleasure to be here and to speak with you. As Steve mentioned, we're going to talk about today mostly about the Data Games project, which is an NSF-funded project, and it's a collaborative research project. So we have pieces of the work going on both at Bill's site out in the San Francisco area and at UMass Amherst. And very briefly, the Data Games project involves, one component that involves designing simple computer games that students play, which we keep the data from and make available to the students for analysis, and in the hopes that they can improve their play of the games for analysis of that data. And I'm just going to give some background about work leading up to this, and then Bill is going to talk more specifically about the Data Games project. Steve already just mentioned a bit about the two pieces of software, Fathom, that Bill and his team have created over the last 17 years, and focuses on real focus area on teaching of math and science and statistics at the high school and introductory college level. TinkerPlots, which I've been working on for about 11 years, focuses on middle school and mostly just data analysis. There's a bit difference in these two tools, but they're related in that when we decided to develop TinkerPlots, Bill convinced us to develop it on top of the Fathom platform, which in my judgment was a wonderful decision because it had allowed a number of opportunities, including the fact that we could really focus on the pieces of the software tool that were important for middle school and not reinvent functions like printing and save and the document structure and dynamic data, and I could go on about the features of Fathom that we could start from on day one. But given the history of these two projects, the natural questions is, well, why the Data Games project? Why this is the next step in this journey, this collaborative journey? And I want to provide at least one set of answers from my perspective, and I think Bill's story would be a little bit different. But from two issues that I've been working on for 20 years or more in interpreting graphs of data involve these two issues. One, sort of the readability of graphs, and from one perspective, trying to produce both graphs and instruction that helps students simply be able to decode graphs, to read them. And the second major objective has been to sharpen or hone students' perception of statistical features in those graphs. And these are two problems I want to talk a little bit about in preparation for thinking about our objectives in data games. Just as a quick example, if I show you this histogram here, and these are reaction times of people, oral reaction times, how quickly they can respond to an auditory stimulus. If I show this graph to young students, I might be interested, for example, in whether or not if I pointed to this feature of the graph here, that they could tell me what it was. What does it represent? Oh, these are maybe 60 people who had reaction time somewhere between 18 and 2100s. And that's part of what I mean by simply being able to read that graph. And a lot of research on histograms shows that that simple decoding for many people is very problematic, for histograms anyway. Perception of statistical features, if I show this graph to somebody, I might be interested whether or not they would focus on, describe the shape of that distribution, and especially notice the fact that it's sort of going up against a left wall, and maybe that makes sense that there's a lower bound by which we can't respond any quicker, but in theory no upper bound. So it might produce that shape. It has a certain central tendency, so that the data seem to be centered around somewhere between 18 and 2400s, and it has a certain spread feature. Those are the kinds of statistical features that we'd like to develop in students. And again, there's a lot of research pointing out how difficult it can be in classes all the way even through college for students to notice those kinds of features, or at least to give meaningful interpretations to them. Just exploring the readability issue, data always and should come from somewhere in the real world. So there's some real world event out there, and for some reason we decide to code aspects of that information and capture it in some formal notational system. Here we might be interested in the genders of these people and their ages and heights and so on. In sort of traditional software, the people go home, they go away, what we're left with are these numbers, and then we perform operations on these numbers. So we might take these numbers, for example, and compute a mean height of 69.4 inches. We might use them to generate a histogram. And of course, the important link for anyone making sense of this is try to imagine back to the real world, to those people who are now probably gone, and relate that to interesting questions about the real world, and ask yourself what the data tell you about that. But very often the readability of these kinds of graphs are very difficult for students. So I can't really recognize individuals anymore in this histogram. How many people are between 24 and 26 years of age? Some students looking at this will think each bar represents a person, and is maybe showing me some other feature like their height or something. The mean in particular, what does that tell me about these people? In developing TinkerPlots, we borrowed an idea that Chris Hancock, to my knowledge, first implemented in tabletop. And interestingly, Jim Kaput was a co-PI on that first project with Chris Hancock. And the idea there was to, when we take numbers, instead of going directly to graphs, let's recreate, basically, in a virtual space, elements or icons that sort of stand for these people. Let's recreate them, in some sense, in our space first. And here I've tried to show their gender by color. And then have graphic representations sort of result from arranging these little virtual stand-in people